All right, mathletes, here we are looking at exponential growth and decay in Newton's law. We're going to be dealing with three equations here when dealing with exponential growth and decay. One's for growth. N of t is the number of cells that we have at some time t. N of naught is the number we have at the starting condition. K is our growth constant, and t is our time. For our radioactive decay or a decay model, we're going to see that A of t is the amount of that element at time t. A of naught is the original or initial amount. K is our constant, and t is our time. Notice K is less than 0 for decay, where we saw for our growth of cells that we see a K being greater than 0. For Newton's law of cooling, we're going to see that U of T is the temperature that we have after a certain amount of time. T is our temperature in the environment that we introduce an object. U of naught is the temperature at the initial condition. Again, T, same variable here, the temperature of the environment. K is our constant that will be dependent on whatever we're dealing with. Liquids and solids will cool at different rates so that they will have different Ks. And because we are cooling, again, we see our K being less than 0. Let's go ahead and look at our first example here. So looking at our growth of our bacteria is given by this equation. N of t equals 1000 e to the 0.01 t. So determine the number of bacteria at t equals 0 hours. Well, if we put t into this equation at 0, well, that's 0 times 0.01 is 0, e to the 0 is 1. So we can see that by that, e to the 0 times 1000, well, that's just 1. So 1 times 1000 is 1000. And we can see that from our equation as well, because that's our initial amount of bacteria. So we had 1000. What is the growth rate of the bacteria? Well, the growth rate, again, just identifying in our equation, is that 0.01 growth rate. So if we use our graphing calculator to graph it, we'll get a graph that looks like this, where we're looking at from 0 to 200. We're looking at hours. So this is hours. Okay. And this is the amount of our y-axis is the amount of our cells. So from 0, so we can see here our y-intercept is 1000, and we're looking at to 2500. So that's what we would look like if we were graphing our function. Again, we would just put it into our graphing calculator. And put it into our y equals like that. Make sure we adjust our window, and then we can graph our function. So what is the population after 4 hours? So using my graphing calculator, I know it's going to be somewhere around here. 4 hours. I'm going to find that here. So using my graphing calculator, I can go ahead and hit, because that's an X value, I can hit trace at 4. And I see that I'm going to have a population of 10,040 cells. Okay, make sure I rounded appropriately. I lost my window there. 1040, so we should probably round to the nearest cell, so that's 1041. Okay, let's look at some other questions with this. So when will the bacteria reach 1700? So looking at my equation here, I'm going to have 1700 is equal to 1000 e to the 0.01 t. Okay, so again, identify what we're trying to solve for. That's that t in the exponent. So knowing that I have a variable in my exponent that I'm trying to solve with, I should know that I'm going to try and use natural logs or logarithms here. So First thing I'm going to do is I'm going to pull away my 1,000 and peel that away. So I'm going to divide both sides by 1,000. Okay, what I get is 17 over 10 when I reduce it equals e to the 0.01 t. So if I take the ln of both sides, okay, I'm going to be left with ln of 17 over 10. These will simplify out to be equal to 0.01 t. So that's just the exponent that's left there using our definition of logarithms. So to get t by itself, now I can just divide out by 0.01, divide by 0.01, and then here it's going to simplify out. I'll just be left with t. So my final expression for t is ln of 17 over 10 divided by 0.01. When I do that into my calculator, so I just type that into my calculator, I'm going to get 53.1 hours. Okay. Next piece is when will the number of bacteria double? So if we started at 1,000, our doubling point is 2,000. So that's my final condition, e to the 0.01 t. So divide both sides by 1,000. That's going to simplify out, and I'm going to get just left with 2 on the left side equals e to the 0.01 t. Using my definition of logs, or taking the ln of both sides, that will simplify out, and I'm going to be left with ln of 2 is equal to 0.01 t. Dividing by 0.01, typing that into my calculator, that simplifies out. So then I get that t is equal to 69.3 hours is how long it will take for that bacteria to grow out. Okay, let's look at another example here. So population decline. So in the Midwest, we're seeing population decline is following exponential laws. So here we're saying that we had a population of some region being 900,000, and it decreased to 800,000 from 2003 to 2005. So that was 2 years there. Okay, what will the population be in 2008? So using this, we don't have a K value. We don't have a growth rate, so we need to calculate that. So because we're given 2 conditions, we're going to be able to solve for our K using our equation. So setting it up, our population, our current population in 2005 was 800,000. And our initial population, so that's our N of T, our initial population, N of naught, was 900,000. Okay, and then we have key E. Well, we don't know our K, but we do know our time. Our time was 2 years that it took for that. So now, notice our K is our unknown variable, so we can go ahead and solve. Again, that K is in our exponent, so we should utilize logarithms or natural logs to solve for that. So first thing I'm going to do is divide out by 900,000. So I'm going to get 8 over 9 is equal to e to the k2, taking the ln of both sides, or using my definition of logarithms, I'm going to get the ln of 8 over 9 is equal to k times 2. Divide both sides by 2, divide both sides by 2, and then I'm going to see that k is equal to ln of 8 over 9 divided by 2. Typing that into my calculator, I'm going to see that I get a K being equal to negative 0.059. Okay. Now, using that K, now that I have my growth rate, and it's declining, so I see that my K is less than 0, it's negative. Now, I want to find the population, or potential population, in the year 2008. So doing that, I'm going to use that K value and use my equation that I started with before. So I have my initial population was 900,000. It's going to be E, there's my K, so negative 0.059. And in 2000, this is for 2008. So from 2008 to 2003, we got 5 years. So my T is 5. So plugging that in, that's 5. Okay. So now I can just type this into my calculator, and what I end up getting is that we get a population of 670,000, rounding to the nearest whole number because we're talking about population of people, is 670,078 people would be the anticipated population of that region. Okay, let's look at our final example here. So Newton's law of cooling. A thermostat reading 72 degrees is placed in a refrigerator where the temperature is a constant 38 degrees. So our T, our temperature of our environment, is 38 degrees. F, our initial temperature, is the temperature that was reading on the thermostat. Okay, so we don't know our K and we don't know a T. But here, the first one, the thermostat reads 60 degrees after 2 minutes. What will it read after 7 minutes? So using this piece of information, let's go ahead and solve for our K because we're given a condition now. So 60 degrees is going to be our U of T, and 2 minutes is our time. So plugging all those pieces in, I'm going to get 60 is equal to 72. I'm sorry, 38. That's our initial, our constant temperature. So 38 plus 72 minus 38 e to the k, and our time was 2 minutes. So simplifying this out, I'm going to get, well, let's just subtract 38 first from both sides. Okay, so doing so, I get 22 is equal to 72 minus 38 is 34. E to the k 2. Divide both sides by 34. This will reduce to 11 over 17 equals e to the k times 2. Doing the ln of both sides, using my definition, I see that I'm going to get the ln of 11 over 17 equals k times 2. Divide this side by 2. Divide this side by 2. Yes, that's a 17. Then we're going to see that k is equal to the ln of 11 over 17 divided by 2. We plug that into our calculator. We are going to get a k that is negative 0.218. Okay, so now I can use that to answer some additional problems. So how long will it take before the thermostat reads 39 degrees? Okay, so let's use this to solve, so I got 39 is equal to 38 plus 34, which was 72 minus 38. And then E, now I know my K, I'm going to use that from before, is my negative 0.218, and I'm trying to figure out how much time that it's going to take to get to 39 degrees. So subtracting 38 from both sides, 1 is equal to 34 e to the negative 0.218 t. Dividing both sides by 34, I'm going to get 1 over 34 equals e to the negative 0.218 t. Using my ln's, okay, I get ln of 1 over 34 equals negative 0.218 t. Divide that to both sides. And if I type this into my calculator, I'm going to see that I get that time is 16.2. And since our time in this case is minutes, so let's take 16.2 minutes for our thermometer to get down to 39 degrees. So I can go ahead and use my graphing calculator to graph the relationship between the temperature and time. Okay, so go ahead and take a second to put that into your calculator. So here you can see I've got this into my graphing calculator, into my y equals. I've adjusted my window. So x is my time, so I'm going from 0 to 20 minutes. Y is my temperature, so 0 to 100. And I hit graph. So I can see that my thermometer is getting colder and colder and approaching that temperature of the cooler. And eventually it's going to bottom line out. And that asymptote that it reaches is that 38 degrees, at which it's never going to get colder than the temperature that it's in. It's the refrigerator temperature. So using our graphing calculator, we want to determine the time needed to elapse before the thermostat reads 45 degrees. So intersect tool, that means on my y2, I want to put 45 degrees. So we could solve this algebraically, but this is a nice trick or workaround to use our graphing calculators to help solve these types of functions. So we see that we graphed that y of 45. So now our intersect is here in calc. So we do second, calc, 5, intersect, and I want my first curve is my function, which is defined on the top left, and I'm going to hit enter. My second curve is here at the line, so I hit enter. And my guess is just to enter because it has one intersection. So I'm going to see after 7.2 minutes, or 7.25 minutes, is how long it will take for the thermostat to get down to 45 degrees. What we notice with our big, and as we trace and go to large temperatures, as we look out at our function and we chase large temperatures, we see that it gets very, very close to 38 degrees and closer as that we trace out larger values of x. That concludes our notes today. Go ahead and highlight any questions you have and bring them to class.